Mr. Shaw, you may begin.
Okay. All right. Jonathan, thanks for showing up. Sorry about the confusion with the arrangements, but let's go ahead and get into it. This is the Introduction to Temperature Measurement, FGO5, Week 2. During this presentation, because we did start a little bit later, we're going to probably curtail some of the time available for questions. You should have gotten a copy of the presentation. We will try to have some questions. You did get a Zoomling survey, and for participating, you're going to get 1.5 professional development hours. We're going to probably not go to total of 90 minutes because I don't think we're going to need as much time for Q&A, but I'm going to certainly cover all the material. Please note you are in a list mode, and until we get to the Q&A session, you really can't ask me any questions, so just hold on until we get to that point. And there's some instructions in here, should be in your copy, about how to go ahead and ask questions when we get to that point. Now, I'm Tim Shaw. I'm going to be teaching this thing today. I've got a lot of experience in process control, and I hope I can demonstrate that by doing a good job on this presentation. So, over the next roughly 90 minutes, we've got a lot of information to talk about. We're going to cover today the second part of this series, and today the discussion is going to be on basically the measurement principles, the types of instrument technologies used, and the applications to process conditions for temperature measurement. You know, temperature is one of the most basic physical properties of matter, and it's a very common parameter used in industrial processes, everything from the tempering of steel to, baking of bread. So let's go ahead and get into the first section. So in this first section, we got a variety of different topics to cover. We're going to start by talking about the principles and the types of issues associated with measuring temperature and controlling temperature. We're going to talk a bit about the different classifications of, I'm going to use the word thermometer, but I'm meaning that in the terms of devices that can be used to measure temperature, not necessarily the thing you stick under your tongue when you're sick. We'll talk a little bit about temperature scales. We discussed those a bit in the first lecture. And we're going to talk about some of the physical properties that can be measurably altered by temperature and temperature changes, and thus be used to determine temperature, including things like liquid-filled and vapor-filled systems, and also mechanical devices like bimetallic elements that can be used to indicate temperature. So let's start off by thinking about temperature measurement. A very common temperature measurement and control example that all of us should be pretty much familiar with is trying to maintain a proper temperature, especially now that it's winter, in our homes or in our rooms. And this diagram shows a simple example. And we have a room, or it might be a series of rooms, in which air circulates, and we have a furnace that can be turned on and turned off to generate and produce hot air that can be brought into the room to maintain the temperature. And in the room somewhere, we will mount a device called a thermostat. And the thermostat is actually a multi-purpose device. First of all, most thermostats have some kind of a dial on them or some kind of a user interface that allows you to set a desired temperature. As we talked about in the last lecture, something called a set point. This is where you say, I want the room to be, for example, 70 degrees Fahrenheit. So you dial in 70. And then inside the thermostat, there's a sensor device. In older ones, it would be a bimetallic strip. In new ones, it's probably a thermistor. And it makes a measurement of the temperature in the room, and very simply put, if the temperature is below the desired set point, then it sends a control signal, typically a contact signal, to the furnace that says, turn the furnace on. And then as heat and hot air enter the room, and the thermostat detects that the temperature has come up to 70 degrees, it tells the furnace to turn off. As we discussed in the last lecture, this is simple on-off or bang-bang control. Now, once we have the room to the desired temperature, you'd think it would just stay there, but it doesn't, because we have a variety of sources of disturbance in our process. For example, if there are people in the room, I guess somebody once said that the average person generates about as much heat as a 75-watt light bulb. And, of course, in the room you may have lamps and lights. So you may have sources of heat that would tend to bring the temperature up. Also, of course, unless you have a perfectly insulated room, and almost nobody does, and you've got windows and doors and things, then you're going to have loss of heat. You're going to have heat loss through the walls, through cracks in the windows. So we're going to have a situation here where the temperature doesn't stay exactly where it is. It's going to cycle up and down a bit. And this doesn't seem all that complicated. But actually, if we really break what we're trying to do here down and think about some of the considerations, there's some very serious aspects we have to deal with in order to do this thing properly. One of the obvious points is that we've got a large room here, or maybe we have several rooms in the house, and they're all being kept at the right temperature by a single measurement point. I know about you, but in my house, my thermostat's in one particular room, and that room is always rather comfortable. And I've got other rooms that are always a little too hot or a little too cold because it's not making the measurement there. So that brings us to some of the issues we have to think about. And in the case of heating the room, some of the things and issues to be considered are, for example, where do you mount the thermostat? First of all, do you mount it way up high towards the ceiling? We know that hot air, rises. Do you mount it down near the floor? Do you mount it on a wall that, for example, is near the vent so that as hot air comes pouring out of the vent, the thermostat feels it immediately and thinks the room is just fine? Or do you put it as far away from the vents as possible? If you want it near windows, do you want it near doors? If you've got a place where sunlight can shine in through a window, then the thermostat may get an incorrect reading. What kind of device are we using for measurement? How accurate does it need to be? What temperature range? We probably are not measuring from, hundreds of degrees below zero to hundreds of degrees above zero in our room. So therefore we don't need a very wide range measurement device, but we want it reasonably accurate. I mean, if the thermostat, for example, is off by plus or minus 1 degree, maybe that's not a big deal. But if it's off by plus or minus 5 degrees or 10 degrees, then the room's never going to be comfortable. Also we have to think about what causes the room temperature to vary, these disturbances I talked about. Also, do we want the thermostat turning the furnace on and off, because of a slight variation in temperature? We drop a quarter degree below that 70-degree target, or do we want to have a dead band? We want to allow the temperature to drop or go above the desired set point by some amount, maybe a couple of degrees plus or minus, before we kick the furnace on or back off again. So these are all different issues that have to be thought about when we talk about something as simple as just heating a room. And these same kind of issues about placement of sensors, types of sensors, accuracy of sensors, are all very important considerations when we talk about making measurements in an actual industrial environment. Now, the simple definition of temperature is it is a measurement of the heat energy of a substance. That substance could be liquid, solid, gas. When we say heat energy, when we talk about a temperature of absolute zero, then in theory this is a temperature at which there's no heat energy at all in the material. When we measure temperature, we can do it a couple of ways. The most common way of measuring temperature is to take the sensor element, whether that's a thermometer itself or we haven't talked about them, or RTD or thermocouple, and actually place them in contact with the substance, whether it's a liquid or the metal case of an electric motor. Whatever we're trying to measure, we can usually make the measurement by placing our measurement device in direct contact with the thing we're measuring. But one of the other ways is by radiation. By definition, heat is a form of electromagnetic radiation. It's actually a light frequency. It's infrared. We can't see it with our eyes, but it in fact is there. And if you hold your hands up in front of a stove that hasn't gotten quite hot yet, an electric stove, you can still feel the heat coming off it. And then as the temperature of the burner gets hotter and hotter, the burner goes from a dull, dark red to a brighter red to an orange, and if you got enough heat through it, it would get bright yellow and even bright white, at which point it would probably melt. But the point is the temperature of a device or of a material can be detected without contact by looking at the actual frequency or wavelength of light emitted by the device. And actually in process control, there are many cases where we can't take a direct measurement. For example, if we're trying to measure the temperature of molten steel in a vessel, we can't really just stick a thermometer in there. We generally will take that measurement by looking at the actual frequency of light being produced by the molten steel, a technique called optical pyrometry. Now, measurement of temperature is important. It really is a key process of measurement. For a lot of materials, their characteristics change based on temperature. And I'm not just talking about whether solids melt into liquids or liquids freeze into solids or become gaseous. The characteristics of many different materials physically change. Certainly, we have density changes with temperature. If you take a liquid and heat it up, it becomes less dense. Cool it down, it typically becomes more more dense, all the way to the point where it becomes a solid. And of course, we have the three different states of matter: solid, liquid, gas. As a kid, I always said, and plasma is the fourth state of material, but we don't generally deal with that. But solids, liquids, and gases, in most cases, a material will transition through those three states based on the temperature. And of course, it's important to remember a very important principle from your high school physics, something called Boyle's law, which is a rule having to do with gas. The old equation was PV is roughly proportional to T, or the pressure times the volume of a gas is roughly proportional to its temperature. So if you increase its temperature, you will change either or both its pressure and volume. And we can use that characteristic of a gas, for example, or a liquid, as a way of making a temperature measurement. Now, when we talk about measuring temperature, basically measurement of temperature, devices that are used for that, come in two general types: a device that has an absolute measurement of temperature or a relative measurement of temperature. When I say absolute, things like optical pyrometry, where we are actually looking at the frequency of light emitted by a hot object, that frequency of light is absolutely tied to the temperature of that material, so that is an absolute temperature measurement. On the other hand, we quite often have what are relative temperature measurements. In other words, the temperature we're measuring is not an absolute measurement, it's that we have increased by or decreased by a certain amount. And this is really how the thermostat in your room works. It doesn't measure an absolute temperature. We just know that that spring inside the thermostat will bend a certain number of centimeters based on increasing its temperature so many degrees plus or minus. Also, measurement devices for temperature fall into two broad categories in the way they work. It really has to do with the sensor technology and the physical properties that we're looking at. Quite often we use a mechanical device or an electrical device for temperature measurement. By that I mean something that mechanically changes. For example, it may physically change, like bending or twisting or expanding in size. Or it may be a pressure change. For example, I may watch the volume of a fluid change by temperature. Or we can have electrical properties. And in fact, the most common way of measuring temperature, things called RTDs and thermistors, are electrical devices that have electrical measurable properties like resistance or the voltage that they generate. And these can be measured. And also, of course, in some cases, we classify temperature measurement devices by their physical construction. Mainly that has to do with their ability to be used in heavy-duty applications. Now, in the last lecture, we did mention that we have several different measurement scales of temperature. The one that we've tended to use for years in the United States is the Fahrenheit scale, which indicates that water freezes at 32 degrees and boils at 212, and therefore absolute zero is at minus 459.69 degrees Fahrenheit, which is kind of a crazy number because you'd think that absolute zero should be zero, which is why we also have the Rankine scale. And the Rankine scale on the far right is really the Fahrenheit scale adjusted so that absolute zero is zero, so that water boils at 491 degrees and freezes at, freezes at 491 and boils at 671 degrees. In Europe and in most scientific applications, we tend to find ourselves using the Celsius scale, or degrees C. This is also called the centigrade scale, and the reason is that it takes the temperature of water freezing and water boiling and treats that as 100 graduations, which is why water freezes at 0 and boils at 100. So centigrade or 100 points of differentiation. And in that particular scale, absolute zero is minus 273 degrees. Kelvin is essentially a way of adjusting that scale downwards and correcting it so that its absolute zero is at 0. But again, in all cases, we're making the same measurements. We're just calling the same temperature by different numbers based on the scale that we're using. And of course, all these scales can linearly be converted from one to the other. Now, how do we measure temperature? There's a lot of different ways. Most measurement of temperature is inferential or indirect, meaning the physical property of a sensor element is altered in a particular manner by the exposure of that sensor to temperature changes. And a thermometer is a good example. A thermometer essentially is a long, very narrow glass cylinder, shall we say, with a tiny little, hollow part in the middle. And at one end, there's typically a bulb filled with some liquid. Most of us have seen thermometers that are filled with mercury, but they don't have to be. And in fact, the ones you use at home these days don't contain mercury because that's kind of dangerous if somebody breaks it and swallows it. But essentially what we've got here is a column of liquid, and what happens is that if you immerse the bulb into something, a hot liquid, for example, at home, if your wife or mother, girlfriend, whatever, is a cook, they may need to control the temperature of a liquid, and bring it up not quite to boiling, or maybe you're canning, you've got to maintain the temperature at a certain level. So you submerge the bulb of the thermometer into the hot liquid, and that liquid, based on the temperature, expands. Again, it's an expansion coefficient. Most liquids and gases definitely will expand when they're heated, and that expansion pushes some of that liquid, some of that fluid up the column, and the amount of expansion will determine how high up the column the liquid will be pushed, which we can relate to a temperature. And that's why on a thermometer, typically you have a graduated scale, and you have this bulb, and if you heat the bulb, like sticking the thing under your tongue if you're sick, then the liquid expands. We can make some calibrations and determine what the temperature reading should be for certain column height of liquid. But again, we're not making an absolute measurement of temperature. The thermometer doesn't really tell us temperature. What we see is that the column of liquid rises a certain level based on increasing the temperature of that liquid by a certain amount. Now, even with thermometers, we have to be very careful how we use them. Because using the thermometer improperly means you'll get an incorrect reading. Remember, as I said, the purpose of a thermometer is typically to heat the bulb at the bottom of the thermometer and let that liquid inside expand and push upward through the column. Most thermometers have a line painted on them. It's usually called the immersion ring, and that basically says do not put the thermometer any further into the liquid, but also don't put it less than that into the liquid, because we want an exact amount of the liquid in the bulb and in the body to be exposed to the higher temperature. In other words, if you put the thermometer too far in, then more of the liquid is exposed to heat, and the column of the liquid will rise higher, and you'll get an actual incorrect temperature reading that's too high. Whereas if you don't stick the thermometer in far enough, not enough of the liquid in the thermometer will be heated, and the column of liquid won't rise far enough, and you'll get a temperature that's actually lower than it ought to be. Now, having said that, there are thermometers made in a couple of different ways. There are thermometers made for partial immersion. That's the ones where most of us are used to it. There are some that expect complete immersion, and the difference between partial and complete, partial means just the bulb at the bottom line. Total immersion really means down to the immersion line, the immersion ring. And then there's complete immersion, where the thermometer is actually completely put into the liquid, but that's far less common. Thermometers are very accurate. If used properly, they in fact give a very precise reading because they work off of a consistent physical property. The expansion coefficient of mercury doesn't change from day to day. So we can use thermometers. In fact, in a lot of laboratory environments, thermometers are used for calibration of other measurement devices. But thermometers are not terribly useful because basically they're a manual measurement device. Someone has to stick it in, hold it, and then pick it back up and look at it and read the measurement off of it. And I guess it would be possible to put some type of photoelectric sensor system onto a thermometer to make it automatically read, but we've devised better ways through the years of actually doing that. And one of the first ways of actually making a temperature measurement that gave us something we could use for remote indication was to use a liquid-filled thermometer system. Now, the way this thing works is we have a pipe, and this pipe can be very short or could be very long, and this pipe at one end has a bend in it, a semicircular bend, an arc, and the pipe is completely sealed. So we've got this C at the top end of the pipe. In fact, this design used to be called a C-tube or Borden tube after its inventor. At the bottom of the pipe somewhere, we have a reservoir filled with liquid. It could be filled with, mercury as indicated here. It could be other types of liquids. But basically, the entire pipe is completely filled with no gas inside. It's totally liquid filled. And the bottom part, this bulb at the bottom, this is immersed into the liquid that you're trying to measure the temperature of, not the rest of it, just that bottom part. Now, that column that goes from the bulb up to the C tube doesn't have to be a couple of inches long. It could be many feet long. It could be dozens of feet long. But somewhere along the line, the C tube part of it at the top has to be mounted and held in place rigidly at the bottom part of it, the bottom part of the C. But the top part of the C, where we have this interesting little connection over to a pointer, that has to be free to move, because what's going to happen is this. As the liquid in the bottom of the tube is immersed into something hot, that liquid, be it mercury or some other liquid, is going to expand, just like it would with a thermometer. Because the area of this tube is fixed, the liquid can't actually expand or change the volume, and so because the volume can't change, the pressure is going to increase. So what's going to happen is we're going to have an increase in pressure inside this sealed tube arrangement, and the increase in pressure is going to be directly proportional to how hot the liquid is. So hotter is going to be more pressure. Now, that C-tube design is kind of interesting because it makes use of another physical property. The metal of this pipe is consistent. It's all the same kind of metal, and therefore, when you heat a metal up, it expands. It's called the coefficient of expansion. But in this C design, what we've created here is an arc, and the outer length of the arc is longer than the inner length of the arc. Because of that, there's more metal, shall we say, in the outer part of the arc, and therefore, as we heat, the outer part expands more than the inner part, and what that actually causes is that C tube bends. Not a lot. We're talking about, movements in millimeters, but if you take that movement and use it to move a pointer, and then, again, the pointer itself is sort of a lever and fulcrum arrangement, we can make a very tiny movement of that C tube actually generate a large movement of that pointer. And the movement of that pointer can be literally making the pointer on a gauge change, or that physical movement could be used to generate a varying electrical signal to send the temperature measurement somewhere far away. So what we've got here is a very basic temperature measurement device that works off of the basic physical principle of the increase of the pressure of a liquid in a fixed volume based on raising or lowering its temperature. And then, as I say, the C tube part up at the top, the Borden tube, will make small amounts of bending in and out based on the pressure change, and that can be used through mechanical couplings to indicate and move a pointer or some other device that can give us an electrical signal so that we can remotely send our temperature measurement somewhere else. So Borden tube measurements, and these were a very common measurement device for many years. Now, instead of a completely full liquid-filled tube, another possibility is to only fill the bulb at the bottom with a liquid that is actually quite volatile, that vaporizes very quickly when you heat it up, and then use the vapor pressure to cause the same thing to happen. So instead of a full liquid-filled tube, we could use vapor. For example, in the prior diagram, we showed this whole contraption being filled with mercury. Well, we all know that mercury can be a bit dangerous to work with. If we were to accidentally overpressure the bulb, we might actually burst the pipe somewhere and have liquid mercury spraying all over the place, which would be a bad thing. So instead of mercury, we can use other liquids, and we can use liquids that are volatile that vaporize, and again use the vapor pressure of the gas that flows up into the tube to have the same effect of bending and warping that C tube or Borden part. Actually, there's three categories of filled systems, of Borden tube type systems. There's the type that are fully liquid filled, the type that use vapor, sort of a vapor-liquid combination. The bulb at the bottom is filled with a volatile liquid that will vaporize. And then there are versions that are completely gas-filled. They have no liquid in them at all. It's totally gas. The important differences between these designs have to do with a couple of factors. An important one is range. If you look at the liquid-filled, you'll see that liquid-filled can go down to lower temperatures than the other types. On the other hand, if you need to go up to higher temperatures, gas-filled tend to allow you to go to a higher upper temperature range. There's also an issue of speed of response. If you look down at the limitations, the liquid-filled has an advantage. It's not, the liquid-filled has a disadvantage. It's affected by ambient temperature. In other words, since the entire tube is filled with liquid, if the C-tube portion that's not submerged in liquid is exposed to an ambient temperature that rises and falls, that is also going to affect the liquid in the C portion of the tube and cause it to have an error, an offset error. So we can have a slightly incorrect reading because of the ambient temperature, and there has to be some form of correction or compensation made. Whereas the liquid and vapor-filled types of C-tubes don't have that problem of being affected by ambient, but they are very slow to respond because you've got to build up a certain amount of pressure, and it's got to propagate through the pipes and up through the C-tube before you see it. So you don't get a rapid response to temperature changes. So there are pluses and minuses in all of these. And all of these work off the basic notion of changing a physical principle like a pressure or volume of a liquid. Now, another type of physical measurement device is something called a bimetallic thermometer or a bimetal strip. As we mentioned before, in the case of a C-tube, if you take metal and heat it, it will generally expand. If you cool it, it will contract. Well, not all metals have the exact same coefficient of expansion. So if we take two different types of metal, one with a high coefficient of expansion and one with a low coefficient of expansion, and we force them together, weld them together, and then heat them, one of the materials is going to expand a lot more than the other, and it's going to cause the material, the strip of metal, to bend. This warping effect can be put to our use. In fact, a bimetal strip in a spiral is commonly used in most thermostats in our homes. Today, if you have a meat thermometer, the type of meat thermometers you can buy at the store to stick into your pot roast, it's quite common that inside that little meat thermometer, if you were able to open it up and look inside, you'll find a bimetal strip wired or wound around in a spiral. And again, what happens is that one end of that spiral is fixed to the side of the tube, and the other is allowed to rotate. And it rotates a vertical shaft that has a pointer at the top end. So as the temperature goes up and down, that spiral of bimetal will twist or rotate one way or the other way, again, indicating a temperature change. So bimetal is another way of using a physical property to get a way of indicating a temperature, not an absolute temperature, but a change of temperature. Now, we use bimetallic strip operations like this in a lot of our devices. For example, if you have a coffee maker and you wonder why, the temperature on the coffee maker that keeps the coffee hot goes on and off and on and off, well, it's a bimetal strip. Thermostats, many of the thermostats that are used, whether it's an electric blanket or any other type of thing where we've got to maintain a temperature, they usually use bimetal strips. Circuit breakers, the types used in your home actually use bimetallic strips to pop the circuit breaker when the current flow heats them up. Motor overloads, if you've got electric motors and you've ever seen one that pops the little red button out, that's actually a bimetallic strip. The directional signals in your car, when you turn your turn signals on and you hear them going click, 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 to blink, blink, blink. Certainly today it's electronic, but in the older days there was a little module, a blinker module, and it worked off of a bimetallic strip. So there's a lot of uses for bimetallic type of technologies. Now, when we think about using, mechanical schemes, we have to think about, what they can and cannot be used for. And in the case of bimetallic, in most applications, we're talking about something where the metal bends a certain amount and is going to close the contact. So basically, they are on or off. Now, they don't have to be. We already talked about using a spiral-shaped bimetallic strip to turn a shaft. Instead of turning a pointer, that certainly could be used to turn a potentiometer or something else to create a variable electrical signal. But for the most part, bimetallics don't give us an easy way to transmit a continuous or analog signal. They're much better at providing contact on-off signals. Now, fluid and gas and liquid-filled systems, these are analog. In other words, a small change will make a small response. A big change in temperature will make a big response. But they do have this difficulty of being slow to respond, as we mentioned, other than the liquid-filled. When we talk about things like thermometers, the accuracy of a thermometer, at least the type that are liquid-filled, are only as accurate as their insertion level. If you improperly insert a thermometer, you will get a reading that's definitely too high or definitely too low. And certainly all filled systems, whether it's a thermometer or one of these, gas or liquid-filled C-tubes, and even to some extent bimetallic devices, most of these devices have some limits to how high and low a temperature they can operate over. In other words, if they're liquid-filled, the liquids tend to freeze. If they're mechanical in nature, if they get too cold, the mechanical aspects tend to fail and the metal gets very brittle. If the temperature gets too high, liquids boil away and metals bend and warp. So they're usually a very limited temperature range over which we can use these things. So they're not necessarily the best devices to be used. And next we'll be talking about some of the kind of devices that would be preferable. So in our first section, we've started off by talking a little bit about some of the principles you have to think about and issues that you have to consider when you are taking temperature measurement. We talked about some of the different types of classes of thermometric devices, everything from, actual physical thermometers and optical pyrometry to using mechanical systems. We've talked about the different temperature measurement scales, and we've talked about the different physical properties that can be used, like mechanical properties and, the gas and liquid expansion properties that can be used as sensory mechanisms to allow us to get an indication of temperature changes. So that's it for the first section. Let's go ahead and see if we've got anybody who'd like to ask a question right about now. So, Newinda, I'd like to turn this over to you for questions.
At this time, if you would like to ask a question, you may do so by pressing star 1 on your telephone keypad. There are no questions at this time.
All right, great. Then let's go ahead into the second section. In the second section, we're going to talk about a different type of temperature measurement device. In the first one, we were dealing with things that used physical mechanical changes, the shape, the size, the pressure, as a way of detecting and determining temperature. In the second section, we're going to talk about electrical devices that have measurable properties that vary by temperature, and these are electrically measurable, like temperature, like resistance or voltage. The types of devices we're talking about, really there's two big ones. Resistive temperature devices, or RTDs. These are devices that, as the name implies, have resistance characteristics that change over temperature and that they are measurable. There's also something called a thermocouple, but thermocouples as well. And we also have something called thermistors, which are actually solid-state devices, and these are devices that also change their resistance based on temperature. All right. To begin with, resistive temperature devices. Essentially, we're just talking about wire, but in this particular case, generally we're talking about wires based on platinum. So these are not something we just throw around. Wire is a conductor. You can put electricity through it, and all conductors have some amount of resistance. Well, it turns out that some metals, platinum is a good example, change their resistance characteristics as you get them hotter or colder. Some of you have probably heard about superconductors. These are metallic compounds that if you bring them down to a very low temperature, preferably not all the way to absolute zero, but certainly at absolute zero, their resistance drops down to pretty much zero, and they become superconductors. Most conductive materials will have, a greater than zero resistance, and some of them, like platinum, you can make temperature changes, small temperature changes, and get very measurable changes in the resistance. So an RTD, in essence, is just a wire, usually wired in a spool around some carrier, like a small strip of glass or mica, to give us a lot of surface, and we send an electrical current flow through this wire, and we measure the resistance change as the temperature changes. The basic measurement circuit that almost all of these kind of things use is something called the Wheatstone bridge. A Wheatstone bridge is a rectangle of resistors, whereas across one set of nodes we can place a voltage, and across the other set of nodes we can measure a current flow. And basically the way it works is all of those resistances, those four resistances, have exactly the same value. Then the voltages balance out and you get no current flow. Whereas if one of those legs varies in resistance, based on the amount of change of its resistance, you will get a current flow. So in this diagram, we have an RTD that is replacing a resistor. It's replacing one of the four resistors in this Wheatstone bridge. And the problem we've got is that the RTD is platinum, and we are going to stick it out somewhere, and we certainly don't want to run platinum wires all the way back, so we're going to have some kind of leads. We're going to have wiring that comes back from wherever the RTD's mounts to our instrument. Well, that wire has a resistance. There's actually, if the wire length is 100 feet and it has so many ohms per feet of resistance, well, then we've got double that because we've got a wire going out to the RTD and a wire coming back. And we've got to correct for that resistance. But essentially that RTD plus its lead wire resistance form the fourth leg in a Wheatstone bridge. And electronically, shall we say, we can adjust one of those resistors to bring the current flow back to zero, and by knowing what the resistance is that we've adjusted, we can now know what the resistance of that RTD plus its legs are equal to, and basically through calibration we can have predetermined the resistance of that RTD over a temperature range, and so by knowing the change of its resistance, we can now calculate the corresponding temperature. Now, when we talk about RTDs, we talk about two-wire RTDs, which is the diagram we just were looking at, three-wire RTDs, and four-wire RTDs. And what's the purpose for all that? Well, as we said, the RTDs quite often are not placed right next to the instrument. They might be hundreds of feet away. And the lead wire that goes out from the instrument to the RTD itself has a certain amount of resistance. And that resistance gives us an error in our measurement. So we'd like to know what that lead resistance is. We could go off and try and calculate it, but again, even copper wire will have a resistance that changes over temperature. So, we can't put in a pre-computed compensation value. The ideal would be to actually make a measurement of the resistance of those leads. Well, we don't want to screw up the RTD itself. We've got a certain amount of current flowing through it that allows us to make a measurement, so we don't want to change that. But one of the things we can do is attach a second lead to one side or the other of the RTD and bring that back and use that additional wire, whose length should roughly be the same length as the other two leads that are actually being used to make a measurement of the RTD's resistance. We can make a measurement of that lead, and then whatever that measurement in ohms is, we double it, and that's the correction factor we have to add to the RTD's resistance measurement, or subtract from, shall we say, because that would correct for the ingoing and return leads of the RTD itself. In most applications, we will see either two or three-wire RTDs. You can use a two-wire RTD very effectively as long as the RTD is mounted very close to the measurement device. And in many cases these days you can buy RTDs where right in the RTD mounting head there is a transmitter device that will convert the resistance of the RTD. It will measure right there, which means that the leads for the RTD are we're talking about inches, and therefore there's not much of a correction that needs to be made. On the other hand, in older applications, we'd see three-wire signals coming back to a measurement device that's a bit further away, and that can make our correction for us. Now, we will also occasionally see four-wire RTDs, and this is, again, where we just have the two lead wires and then two additional lead wires that allow us to make both the measurement of the incoming and outgoing instead of computing it from one lead wire. Frankly, four-wire RTDs are not very commonly used. They're something you're more likely to find in a lab environment where you really need the higher level of precision. They're not something you'll typically see in the process world used out there in a plant environment. One very important thing, though, is you need to understand your measurement instruments. If you buy a device, whether it's an RTD card for a programmable logic controller, or you get an RTD input board on a DCS system, it's important to know whether that is designed to take a 2-wire, 3-wire, or 4-wire device. If you try to wire a 3-wire device into a 4-wire instrument, it will not work. If you try to wire a 4-wire into a 3-wire instrument, well, it's kind of a waste of time. Really, you just have an extra lead that there's nothing to wire it to. So you want to make sure that whatever the instrument device is that you choose, if it's a device that wants a 3-wire, then order a 3-wire. If it wants a 4-wire, order a 4-wire. Okay. Now, I've been mentioning RTDs and said platinum. There are primarily 2 types of RTDs used out there, 100-ohm platinum and 50-ohm copper, although 50-ohm copper is far less often used because it's copper and it tends to corrode. So when we talk about RTDs, almost invariably we're dealing with 100-ohm platinum RTDs. And we'll talk in a minute about what we mean by 100-ohm platinum RTD. Now, as I said, an RTD really is nothing more than a long length of wire that we will then expose to our temperature. So in this diagram here, we're showing a couple of different physical ways of building them, but the most common one these days is where you have this glass body where the platinum wire is just coil wound on a glass substrate, and the whole thing is sealed in glass. And this picture is much larger than scale because actually this RTD tip itself is a fraction of an inch in length in size. We don't need a whole lot of surface area. But the reason for winding the platinum wire on the glass body in a coil like that is to expose as much wire as possible to get the biggest effect of the temperature change in the electrical characteristics of the material. Of course, there are also ceramic RTD manufactured devices for applications where you need even higher temperature than you'd want to deal with things that are in glass. Now, RTDs themselves have to be physically protected. They are easily broken. So generally, an RTD will be purchased that is maintaining some type of a protective sheath or a probe. You'll find lots of different words used, but effectively, you generally order an RTD that comes mounted inside of a thin metal probe device that provides physical protection of the RTD. The RTD itself is rather delicate. It's easy enough to break or crush, so we don't really want it exposed to turbulent liquid flows or material that might be sloshing around and damaging it. So we usually put these things inside of some type of a metal probe, quite often stainless steel, and then the RTD itself is supported and structurally reinforced by having that probe filled with something. It could be filled with powder or cement. It could even be filled with some type of liquid gel. The important point is that this is to provide mechanical protection of the RTD. It does introduce a little bit of an issue because obviously the RTD itself is not directly in contact with the liquid that we're measuring, for example, the temperature we're measuring. So there is a small time lag, but it's usually a rather small one because we're really not talking about a large physical area here. So it slows response a little bit, but generally that's not much of a problem. Now, as I mentioned, RTDs, especially, if they're placed a long distance from where the measurement instrumentation is located, we have this problem of correcting for their lead error. Today, in fact, it's much more common when you buy an RTD for an industrial application that it comes built in together with both the metal probe to support it and also in the head that usually mounts onto the side of the tank or wherever you're inserting the RTD into. With a conduit fitting, there's circuitry inside there, right there, generally, to convert the RTD to some other signal. A very common thing would be to have a transmitter element right there in the head of this assembly that would turn the RTD's resistive measurement into a 4 to 20 milliamp signal. And because you're talking about an RTD whose lead length now is, maybe somewhere between 6 and 12 inches, there's very little correction necessary. But the circuit card will make those corrections. And today, in fact, we see smart RTDs, and later on we'll be talking about thermocouples. We see smart thermocouples where what comes out of this device doesn't even have to be a simple electrical signal like 4 to 20. It could be a serial communication link, talking Modbus or field bus. So more and more we're seeing smart devices. In fact, it would not be uncommon today that this circuit card that we're looking at here has a little antenna sticking out of it. In fact, we will find a lot of our smart RTDs and thermocouples now are wireless devices. So you don't actually wire any signaling to them at all. You just talk to them using the appropriate wireless technology out there, for example, wireless HART. Now, when we talk about RTDs, there are certain considerations in using them and picking them. First of all, because of their mechanical construction, they're very stable. They don't have any real need generally for any kind of calibration, not that there's any screws you can turn or something. They usually will drift in accuracy less than a fraction of a degree C over 5 years of operating. They generally do provide a pretty linear output, so their resistance change is very linear over their temperature range. We haven't talked about thermocouples yet, but we're going to discuss them in a minute, and we're going to talk about something called a co-junction reference. Well, RTDs don't deal with that. They strictly are a device that's resistance is going to change based on temperature. They do have this issue for lead resistance compensation, but you can do that if you have a three-wire or four-wire RTD, or if you keep the leads extremely short by having a smart-type RTD device. They can support a wide range of temperatures. You can go, minus a couple of hundred up to several hundred, 650 degrees C. There are a couple of standards out there. We talk about a 385 or 392 platinum, and those numbers are actually what they stand for is 385 means 0.00385 ohms change per degree C. They're called 100-ohm platinum RTDs because typically enough wire is wound to give them a basic resistance of 100 ohms at 0 degrees C. So that's your starting point. A platinum 100-ohm RTD should have a resistance of exactly 100 ohms if you cool it to 0 degrees C. Or in other words, stick it in an ice cube, it better read 100 ohms. So, again, devices change their electrical resistance based on their temperature. Now, another device that also has a resistive component that varies based on temperature is something called a thermistor. This is a relatively new device. It is a semiconductor device. It's not based on wire. It's based on the same sort of materials, doped silicon and such that are used inside transistors. They do have an electrical resistance that varies greatly as temperature changes, but they generally have a limited temperature span. Thermistors are best used in the kind of temperature extremes that a human being feels comfortable in. And they're very comfortable, being used in HVAC applications. But you certainly can't use them at extremely high or low temperatures, no more than you could any other electronic device because they'll burn out. They're very low cost. I mean, they can be bought for pennies practically, and they can be manufactured in a variety of different shapes and sizes. They are very accurate and stable. But again, low to medium temperature ranges. They have a much greater change in resistance per degree of temperature change than an RTD does. And again, they can be manufactured in a variety of shapes and forms. And in fact, thermistors are quite often embedded in electrical circuitry. If you ever wonder, how your computer, for example, knows that the circuit card inside the memory card or the processor card is getting too hot, well, that's probably because it's got a thermistor mounted on it somewhere in some circuit that's measuring its resistance to make a temperature determination. Again, thermistors are manufactured in a variety of shapes and sizes. They're usually glued to devices. And again, they can be very, very tiny. They can be, the size of a small, not quite pinhead, but a tiny little bead. All right, so we've talked about RTDs, resistive temperature devices, as a general category of sensor device whose resistance varies by temperature. We said that the most commonly used RTD-type device is the platinum 100-ohm RTD, which can come in a 2, 3, or 4-wire configuration. Again, 2-wire means you keep the lead wires very short because they do have resistance and you have to correct for it. If you can't do do that, then you go to a 3-wire RTD where there's an extra lead that allows you to measure the resistance of that lead. Or if you're in a laboratory environment, you might even use a 4-wire RTD. We've talked about how RTDs are mechanically very delicate, have to be protected and sheathed, usually inside a metal probe of some type. We've talked about some of the issues of deciding, whether you can use or how to use an RTD, and we did finish up by talking a little bit about thermistors as a different type of resistive temperature device. All right, that brings us to the end of Section 2. Nwinda, let me turn it back to you to see if there's any questions.
At this time, if you would like to ask a question, you may do so by pressing star 1 on your telephone keypad. And there are no questions at this time.
All right, let's go forward and get into Section number 3 and finish this thing up. In Section 3, we're going to talk about another electrical type of temperature measurement device, but something called a thermocouple. In the prior section, we talked about devices that have a measurable electrical property of resistance and the fact that they vary in resistance based on temperature. Here we're going to talk about electrical devices that have a completely different principle. Here we're going to deal with something that generates a voltage potential that will vary based on temperature differentials. So we're going to start by talking a little bit about how thermocouples actually work. We're going to talk about the different types of materials, the need to use something called extension wire, something about their construction and their usage, and a little bit about calibrating thermocouple transmitters. So, thermocouples. Basically, if you take two different types of metal and you turn them both into wire and you twist them together and put them over a heat source, basically you will generate a temperature differential that will produce a voltage differential. And in a simple example, if I literally take a couple of feet of two types of wire and twist the ends together at one end and the ends together at the other end, and then stick one end into something hot or cold, there will actually be a current flow generated through the wire loop. And if I were to take a very high precision electrical measurement device and touch it to these two different junction points, I would actually measure a small voltage, a microvoltage level type signal that would be indicative of the temperature differences between those two junctions. And that's an important point. It's the temperature difference. So we see two junctions here, one at temperature 1, one at temperature 2. The voltage I would measure across this is going to be proportional to T1 minus T2. It's the difference between them, right? So when we talk about making a measurement with a thermocouple, we're talking about measuring temperature difference between one junction and the other junction. Well, we're trying to measure something, but we have two temperatures, and we need to know what one of them is in order to be able to get an idea of what the other one is we're measuring. So when we talk about this, here's a diagram to sort of give this notion. If I were to take two types of metal, and in fact there's a type of metal we all know called copper. There's another type of metal called Constantan, and these two metals have different enough electrical properties that if we create a thermocouple, in other words, crimp a pair of them together at one end and stick it into a heat source, here we're saying thermocouple, and then take the other end of those wires and crimp them together and stick them into a reference, like melting ice. And we know that ice melts and it will sit there generally at a 0-degree temperature. So if we were to do this and measure the current flow around this loop, that current flow would tell us the temperature of this heat source that we're looking at with the end that's inserted into the heat, because we would know that we have a current flow that's generated by the difference between the one junction, which is being held at a calibrated value of 0 degrees C, and the other end whose temperature value we don't know, but we can determine by the voltage or the current flow that's being generated by the difference between the two. Now that sounds great, but in an industrial plant, we can't really have some tank somewhere full of ice that we have to constantly replenish in order to make a temperature measurement. All we need is to be able to know what that reference temperature is. Certainly in a lab environment, using either boiling water or using ice to give us a guaranteed 0 or 100 degrees C reference is one good way of doing some calibration. But in the real world, we can't really use that. In the real world, instead of a bucket of ice, what we really deal with is the fact that the connection of the thermocouple wire at the other end, at the instrument itself, that connection where you screw those wires down on a terminal block, that is your other junction. That is, in fact, your other junction. And what we need to know is what the temperature at that termination point is, because if we know that temperature, and we can make the voltage measurement across this wire, then we'll know what the measuring junction temperature is of the process that we're trying to measure. Now, in the old days, and by that I'm talking about like the 70s when I first got involved in computer-based automation, we didn't have all the technology we have today. One way of achieving this was to use something called isothermal racks or isothermal terminal blocks. And that literally meant that your connection point of the instrument, your thermocouple would land on a large block of metal that was being heated, usually with electric heaters, to maintain it at a certain temperature, at a known temperature, using like a bimetal strip to turn the heater on and off. And having a large block of metal that was heated, as a heat source, would allow us to have a reference temperature that was known, and then we could make the electrical measurement of this thermocouple signal coming in from the field, and by measuring the voltage and knowing what our reference junction temperature is, because we're maintaining that at some value, we could actually determine what the temperature is out at the measurement point. Today, we wouldn't do that. Today, instead, right there at the terminal block where the thermocouple is terminated, if we have a thermocouple input module, for example, for our PLC or for our RTU or our SCADA system, or for our DCS system, on that actual card, right there and adjacent to where the screw terminals are, where you tie down the thermocouple wires, we probably have a thermistor mounted on that card, and that thermistor's temperature is going to vary by ambient, and we can make a measure of the resistance of that thermistor to determine what the current temperature is at the termination blocks on our input card, and use that to make a current adjustment for the temperature correction to let us get an accurate measurement of the temperature we're measuring out there at the measurement point. So today we actually would use something like a thermistor to make a measurement of the junction point where the where the thermocouple wiring actually lands. Now, as I said, if we take two different types of metal and sort of twist them together, we can create a thermocouple, and literally you can do that. Because different combinations of metal have different characteristics, there's a whole set of thermocouple types out there, and they're usually designated with a single letter, types J, K, S, T, R, K, B, E. And the designation, the ISA single letter designation, will indicate to you what the materials are. For example, we were talking about copper constantine in one of the prior diagrams, and the copper constantine is a T-type thermocouple. But different types of thermocouples have different characteristics, because obviously different metals have higher points where they'll melt, lower points where they'll freeze and become brittle. A very, very common thermocouple, the sort of thermocouples you see all the time used in the process world, are the J and the K. One of the reasons is because they're fairly inexpensive, and the other is that they have a pretty good temperature range. As you can see on this diagram, a J thermocouple is just iron and copper nickel, and that's good because copper nickel is quite often a material used in junction blocks. But that can operate from minus 210 up to 760 degrees. That's a pretty good temperature range. The K can go even over a wider range than that, nickel and chromium nickel. So different types of thermocouples exist. They have different characteristics as far as the voltage that they generate. On the average, when we talk about the voltage, we're talking about microvolts. And in most cases, when we talk about the temperature voltage generated by a thermocouple, we're talking about somewhere between about 1 and 70 microvolts per degree Fahrenheit. So we're not talking about large voltage levels. We're talking about microvolts, hundreds of microvolts, between the lowest temperature range and the highest temperature range. But that is something we have the ability to measure today. So again, a wide range of RTD devices based on different materials with different characteristics, which means they're good for certain types of applications because of their resistance to corrosion, their ability to withstand higher temperatures. And thermocouples are very commonly used as temperature measurement devices. For one thing, they're fairly rugged. Now, one of the problems you run into with thermocouples is that every time you land a thermocouple wire on a terminal block somewhere and screw it down, you're creating another thermocouple. If you've got two different types of metals, you create a thermocouple. So if you want to run a thermocouple from some point quite a ways back to your instrument, it's very important that all along the way, the entire circuit is wired up using the same materials as the thermocouple. So if you've got a thermocouple that uses iron wire and chromium nickel wire, then all the way back to your instrument, you should be using, iron and chromium. And in fact, to do that, we have something called extension wire. If you have a T thermocouple, then you use TX extension wire. If you have a K thermocouple or a J thermocouple, you use KX or JX extension wire, because the extension wire is a pair of wires that are made of the exact same materials that thermocouple is made out of. And in fact, thermocouple extension wire usually comes with connections where you can, make a disconnect point, using plugs and connectors. And those connectors and plugs themselves have, two pins and two sockets, and they're made out of exactly the same material as the thermocouple. So if you've got a plug-connector combination for a J thermocouple, then one connection and plug is iron and one is Constantine. So, we use thermocouple extension wire to run our leads all the way back to our instrument. Now, thermocouple extension wire isn't cheap. And in fact, if you have a long thermocouple run, it's kind of a pain in the butt. But as we had mentioned with RTDs, today it's far more common to keep our thermocouple run very short. It's far more likely that, in fact, we'll use a smart thermocouple design where the thermocouple itself is again mounted inside a probe that sticks into a vessel somewhere, and at the head of that probe we'll put the electronics right there to measure the voltage from the thermocouple and convert it to a 4 to 20 milliamp signal or some other type of signal that's transmittable, and eliminate the need for this expensive extension wire. But if you are going to run a thermocouple signal any distance, you have to use extension wire that matches exactly the thermocouple itself. If you get it wrong, you will not get correct readings. Now, the design of a thermocouple is very simple. Here I'm showing three simple little examples. These are greatly expanded. We're talking about something that's actually, in usual case, just an inch or two long. And it's important to note that the actual thermocouple is right there at the tip. So if we look at these three designs, on the far right end, you see what looks like a little loop with a bump on it. Well, that bump is actually where the two pieces of wire come together and are crimped together or, compressed together or welded together. But that little junction right there, that's the actual thermocouple. The rest of it is nothing more than either the two types of wire going back from that junction to the end of the thermocouple where we can make a connection. Again, thermocouples are made from wire, so they're mechanically a bit stronger than an RTD would be, and we have to deal with the temperature characteristics and rigidity characteristics and expansion characteristics of the metals used. That's actually one of the reasons quite often you'll see there's sort of gaps in the insulator beads, because the temperature, as it goes up and down, the wires themselves will expand and contract a bit, and we have to allow for that in design of the thermocouple. Now, in the real world, generally what's going to happen is the thermocouple will be inserted into some type of protective tube. That's usually called a thermal well, or you'll hear people talk about a probe. And that probe is made out of metal. In certain applications, it might even be stainless steel. The length of that probe is usually somewhere between 6 to 12 inches. It can be longer, it can be shorter. The diameter of that tube can be anywhere from a 1/16 of an inch in a rather small tube all the way up to a 1/4 inch diameter, although 1/16 and 1/8 are far more common. The head, the terminal block here, the part of the probe that sits on the outside of the vessel into which the probe is extended, at that point we've got the terminal block where the two leads of the thermocouple end. Quite often today, inside that connection head, we will put a thermocouple transmitter. something that turns the thermocouple signal right then and there to 4 to 20 milliamps so we don't have to use extension wire. Or today it's also becoming more common that inside that connection head we'll have a radio transmitter, and we'll see a wireless thermocouple type device being used. Now, thermocouple calibration, what does that mean? Well, again, because we generally don't want to run thermocouple extension wire all the way back to a control room halfway across the plant because of expense and such, we're going to want to convert that to a 4 to 20 milliamp signal. And that's done with a device called a transmitter. And the transmitter is an electrical circuit in this case that can take the millivolts or microvolts, shall we say, that's generated by a thermocouple and linearize them and put out a corresponding 4 to 20 milliamp signal. Now, one of the things about calibrating a transmitter is we have to pick the temperature range. For example, if we went back a few slides and looked, we'll see that a J thermocouple, as we mentioned, can operate from minus 210 degrees to 760 degrees C. Well, that's great, but if we only want to operate from, let's say, 100 to 250 degrees C, then that's what we want our transmitter calibrated for. We want to take the voltage put out by the thermocouple when it's at 100 degrees C and all the way up to 250 degrees C. We want that voltage range to produce a 4 to 20 milliampere output from the transmitter. So to do that, we've got to adjust the transmitter's zero and span. And this is something we talked about in the prior lecture. But to make that happen, we've got to go through a calibration process. And today, the typical way of doing that is to use a calibrator device. Today, these calibrators are extremely smart. They look like just, amazing calculators of sorts. But it's common today for a calibrator device to be able to put out a simulated microvolt signal that is exactly representative of what a thermocouple would put out. So with a calibrator today, there's a pair of terminals that you can come out of to go from the calibrator to the transmitter, and that terminal pair will put out a microvolt measurement based on the type of thermocouple you like to use. So you tell the calibrator, I'm going to calibrate a GA thermocouple, and you tell it that I want to put out a millivolt or microvolt range for that, GA thermocouple, and then you dial in your low temperature. So in this case, you dial in 100 degrees C, and so the calibrator will put out the microvolt signal that a GA thermocouple would generate were it at 100 degrees C, and that goes into the transmitter. Now, the output from the transmitter is supposed to be 4 to 20 milliamps. So that is wired back into another pair of terminals on the calibrator where we're measuring the milliamperes put out, and we'll adjust the zero and span of the transmitter until we show 4 milliamps when the calibrator is representing 100 degrees C, and we'll adjust it to be putting out 20 milliamps when the calibrator is putting out what would be 250 degrees C. And once we've completed that process of adjusting the span of zero, our transmitter is calibrated, and then we can just hook a thermocouple up to it instead of the calibrator, and away you go. All right, when we deal with thermocouples, again, there are considerations. Thermocouples do tend to drift, and drift is going to depend on the type. Why? Well, because metal ages and its characteristics change over time. You might see somewhere between a couple of degrees to 5 degrees annually in a thermocouple that's being used continuously. The drift is almost always in the same direction. So in other words, you wouldn't see a drift positive 1 year and then drift negative. And again, you can correct for this. You can go back in and do the recalibration. So by recalibrating the transmitter, we can correct for this. Again, one of the things about thermocouples that's nice is they have very high temperature ranges. You can't possibly use things like thermistors or RTDs to measure the temperatures as high as a thermocouple can go. They also can go to very low temperatures. You have to use them properly. Frankly, you have to select the right ones. You have to install them right. You've got to make sure you do the right things with temperature correction, cold junction compensation. The thermocouples also are not necessarily linear. Most thermocouples have a curve that is sort of S-shaped. Over the middle of their curve, in other words, the middle of their range, they're pretty linear, but at the low end and the upper ends of the range, they're nonlinear. So if you have to operate over a wide range, then you have to have some type of curve correction, usually done with some type of a breakpoint table. The other thing about thermocouples is they are, as I said, just a couple of pieces of metal, sort of stamped or spot welded together. Thermocouples have a couple of failure modes. Quite often, when they're used at high temperatures, they'll burn out. They'll literally just burn open circuit. Fortunately, most systems have the ability to make that determination. The other problem you run into sometimes with thermocouples is they will be crushed, and they will actually short out. It's not uncommon in most control systems to have the ability to make a determination of a crushed or burnt open thermocouple. All right, so basic points. Thermocouples are nothing more than different types of metal, pressed together to form a junction, and if we heat that junction and create a second junction at the other end of that wire, then we will get a voltage that corresponds to the temperature differential between those junctions. And if we can know the temperature of one of those junctions and measure the voltage, then we can make an estimation of the temperature of the other junction, our measurement point. Thermocouples are made out of a variety of different types of metals. Based on the type of thermocouple, you've got to have matching extension wire if you're going to run the leads any length or distance. Thermocouples can be constructed in a variety of different ways. They quite often look exactly like an RTD because all you really see is the metal probe and the head end. With thermocouples, again, the very important point is that you can go to higher temperatures and lower temperatures with them than almost the other measurement devices, but they do have a tendency to drift over time a bit more than the other types of technologies. So you do have to deal with things like temperature calibration occasionally to make sure that you keep your thermocouple transmitters calibrated appropriately. All right, that brings us to the end. Before we finish this thing off, we know how many sites that we've got, but one of the things that we want to do in most cases is make a determination of how many people we've got at your sites. So I'm going to pop up a slide here. We'd ask you, please, if you could, to go ahead and click on the appropriate polling choices here to let us get an idea for how many people you've got at each of the two sites. Okay? So if you would, go ahead and click that. I think I've given everybody a chance to do that. So let's go back and sort of finish this thing up. This is the end of the third section and also the end of the thing entirely. So again, Linda, let me turn it over to you to see if we've got any questions.
At this time, if you would like to ask a question, you may do so by pressing star 1 on your telephone keypad. Again, to ask a question, press star 1. There are no questions at this time.
All right. Well, then let me wrap this up. Thank you all for hanging in with us today. I apologize to all of you about the login problems that we had, but I'm glad we were able to reconnect with you guys and go ahead and finish this up. I do want to let you know that the ISA has related courses. The course today is the second lecture in a series of 5, our FGO5 online seminar. But we also have FGO7, which is a very intensive week-long introduction to industrial automation and control, and TCO5, which has a lot of really great labs where we actually tune loops and play with thermocouple transmitters. If you're interested in certifications, the ISA has TS00, which is a CCST Level 1 exam review course if you're looking for certifications. If you're interested, please contact the ISA. As I mentioned, we've got a couple of certifications. It might be useful in your career to have the CAP, the Certified Automation Professional, or the Certified Control Systems Tech certifications. Again, if you're interested in any of these, please contact the ISA. We did provide, as part of the package to you, a Zoomerang web survey. We do take your comments and feedback very seriously. We try to improve our courses and make sure that they've got content that's useful to you. So please, if you get the opportunity, we would like you to answer that question and send it back to us. And on that note, I think we're pretty well done. So again, Linda, I'd like to turn it back to you to finish us up today.
This concludes today's ISA web seminar. Please do not forget to fill out the evaluation survey found in your email inbox. Thank you for attending and have a nice day. Presenters, please hold.